Today, we want to continue our discussion with acids and bases, but talk about a second theory, the Bronsted-Lowry acids and bases. First, let's go back and review. Remember, the definition of acids and bases has been according to what's known as the Arrhenius acid and base theory, which states that acids are substances that produce hydronium ions, which is H3O plus, or we can use the shorthand of H plus. And bases, sorry about that handwriting there, are substances that produce hydroxide ions in water. These are great definitions for some substances, but there are other substances that still have the properties of acids or bases that go beyond this. And that's where Bronsted-Lowry acids and bases can come in. It broadens the definition, broadens the amount of substances that can be called acids and bases. So if I was doing a diagram, so this, let's say these are the Arrhenius acids and bases. So the Bronsted-Lowry include the Arrhenius acids and bases, but includes more substances. There is a third theory known as Lewis acids and bases that we won't talk about in this course, but just to let you know, we can even broaden the definition of acids and bases further. So let's start with the definitions that are helpful in understanding Bronsted-Lowry, and then we'll go to some examples of identifying these. This should be in your notes. If you're using the same version packet I have right now, it's on page 15, but it would be titled Bronsted-Lowry acids and bases. So first of all, proton. A proton is a hydrogen nucleus. So that would be your H plus. And it's a hydrogen atom that's been stripped of its electrons, essentially, leaving just that proton in the middle. And this is helpful because Bronsted-Lowry acids and bases compare an acid and base to whether they donate a proton, that would be an acid, a proton donor, or whether they accept that proton, which would be a base. So base is a proton acceptor. Some substances behave as both acids and bases. Sometimes they give a proton, sometimes they accept the proton. So they act as both an acid and a base, depending on what they're with. As we react an acid and a base, we find that we get what are called conjugate acids and bases. Within these reactions, you will have a conjugate pair. Now, the conjugate pair are two substances related to each other by a single hydrogen ion. Remember that hydrogen ion is the same as the proton or a hydrogen nucleus. In other words, on the reactant side and the base, or the reactant side and the product side, the only thing they differ by is an H plus. So it changes the charge and it adds a hydrogen. Now, the conjugate acid is what is produced when a base accepts a hydrogen. So when the base adds the hydrogen to it, now that is ready in the reverse reaction to act as the acid. Likewise, a conjugate base is a species that is produced when an acid donates the hydrogen. So the acid gives up the hydrogen. What remains is known as the conjugate base. So let's look at an example. In this case, I have ammonia reacting with water to produce ammonium and hydroxide. If we look carefully here, we'll notice if we compare the ammonia to the ammonium, we notice that it has gained a proton, which means the proton came from the water, and it's only one proton, and it was given to that ammonium. We could do the same thing in comparing the water and the hydroxide to determine which is the proton acceptor and the proton donor. So in this case, water is giving the proton, which makes it the acid, and ammonia is gaining or accepting the proton, which makes it the base. Now, if I look on the reverse reaction, so I focus, so it's reverse this way, we can see that the ammonium would have to lose the proton and give it to the hydroxide in order to produce the ammonia and the original ammonia and the original water there. So in this case, the ammonium is the acid or the conjugate acid. The conjugate acid will always be on the products, what appears as the product side of the reaction. And therefore, my hydroxide is my conjugate base. So we can fill this in. The acid is water, the base is ammonia, the conjugate base is hydroxide, and the conjugate acid is the ammonia. Remember, conjugate pair are two species that only difference between them is a proton. So if you look, this, again, let me highlight here. This right here compares to this by the addition of a proton. That makes a conjugate pair. Likewise, your water and your hydroxide only differ by one proton. So one pair is always going to be your acid and your conjugate base, and the other pair is always going to be your base with your conjugate acid. How we list these, you can put it and water and hydroxide. I put a slash here just so you see they're paired up. They differ only by a proton. Likewise, the ammonia and the ammonium differ only by a proton. How do we know which is favored? Well, if I look at the Ka value, it tells me the strength of the acids. I'm going to look up specifically the acids. They are the ones that have a Ka value. If I look that up on the chart, you'll notice that, delete that so it's a little easier, the Ka value for the conjugate acid is stronger. That means you're going to favor the reverse reaction. More of the conjugate acid will ionize than the original acid. Something I want to mention here as well. This particular base, ammonia, actually fits into the Arrhenius definition as well. We react it with water and we produce hydroxide. So both the Arrhenius definition and the Bronsted-Lowry definitions very easily fit here. Let's look at another example. In this case, I have nitric acid and water, and you can see that the water gains a proton to form hydroxide or hydronium. So it has to gain it from the nitric acid. It's going to give it to the water. So the acid would be the nitric acid, and you've got your base is the water. On the other side, the hydronium, to go in the reverse reaction, would have to give the proton to the nitrate ion. So we've got our conjugate acid and our conjugate base listed. So again, we can label these. The acid would be HNO3, nitric acid. The base would be the water. The conjugate base would be your nitrate ion, and your conjugate acid would be your hydronium ion. So which two, compared just by the difference of a proton? Well, you've got two pairs. You've got your acid and your conjugate base, and your base and your conjugate acid. All right, so again, favored reaction. Which one is stronger here, the forward reaction or the reverse reaction? So you have to look this up on the chart. On the chart, we find the Ka of nitric acid is larger. It might even say very large, but it's a strong acid. Hydronium is smaller. It's not actually listed on the chart you received, but you can see 55.5. You should jot that down because that will be used on your homework pages. You can see that it's definitely smaller. So in this case, the stronger acid is the actual acid, not the conjugate acid, but the acid, which means the forward reaction is favored. So when the acid is favored, when the acid is stronger, the favored reaction is the forward reaction. When the conjugate acid is stronger, that means the reverse would be favored. I jumped ahead a little early here, but just to mention as well that nitric acid, when you put it in water, did produce hydronium ions, so it acted both as a Arrhenius acid as well as a Bronsted-Lowry acid. But the other substance that was in both of these cases, the water, in the first case, it acted when it reacted with ammonia as acid. In the second case, the water, when it reacted with the nitric acid, acted as a base. This is an example of something that is amphoteric. Water can act as an acid or a base depending what it is with. Final example here. If we look here, we'll notice as we look through the forward reaction, the hydrogen will leave the proton, will leave the phosphoric acid and go to the nitrite. On the reverse, or which makes the acid, the phosphoric acid, and then the nitrite is your base. In the reverse reaction, we'll notice that the proton will leave the nitrous acid and join the H2PO4 ion. So we've got our conjugate acid and our conjugate base. Notice we have an acid and base here, but we're not putting it in water, so it no longer fits the Arrhenius acid and base definition, but it does fit the Bronsted-Lowry. So again, if we look at this, we can put these in based on what we've written. And you'll notice the pairs, you've got the acid with the conjugate base and the base with the conjugate acid. Now I might not always include this part right here, which is why I tell you in your problems you should be writing the acid and base and the conjugate acid and base underneath the substances. And also do show that movement of the proton. So again, let's look at the favored reaction. If I give you those Ka values, which you could look up on the chart, you'll notice that the acid is stronger than the conjugate acid. That means in this case, the forward reaction will be favored. So you have some example problems. I want you to go through those example problems, label the acid base, conjugate acid, and the conjugate base. List the conjugate pairs, so you're going to skip that highlighted part right there that I have boxed in, just by labeling it underneath, and then determine which is favored, the forward reaction or the reverse reaction based on the Ka. Good luck, and if you have questions, as always, make sure you're ready to ask them. Have a great day.